For this portion of the lab, we examine spherical aberration through a thin lens. First, I want to talk about how spherical aberration occurs and what really is happening as we move through an optical system. So the way we measure spherical aberration is we have our exit pupil outside of our optical system, and we have a reference wave that follows diffraction limited properties. It follows right here and focuses right where the paraxial image focus should be. When we have an aberrated wavefront, such as spherical aberration, we have another spherical wave that isn't perfect as the reference wave. So what happens is it focuses somewhere else other than paraxial focus. In the case of spherical aberration, we have that the spherical wave varies as a cubic, the error, so it looks something like this. But if you see in this area right here, we have pretty close to diffraction limited, so we have rays focusing in the paraxial focus, but as we move further up our exit pupil, our rays begin to focus somewhere else, and they focus actually at the marginal focus. So spherical aberration has the two different focuses, one at paraxial and one at marginal. And this distance right here is known as our longitudinal aberration, and we can actually measure it just as we will be doing in this lab. We have various ways of controlling spherical aberration. We can split the lens, we can shift.
The basic idea of this experiment was we had a laser coming into a pentaprism, and the pentaprism had a degree of freedom so that you could shift the laser and we could make the laser be incident on these different Hartman holes. By doing this, we could control the rays and see where the rays focused at different parts of, say, marginal or paraxial focus. For instance, if the ray hit this hole, it would focus on the marginal focus. And if the ray hit this hole right above the optical axis, it would focus at paraxial focus. For the first step, we sent the ray through here, and we got the microscope and focused it on that spot of the optical axis. Then we moved the beam down by moving the pentaprism, and we shifted the microscope to intercept that ray coming in, and the movement of the microscope gave us the transverse ray aberration. And we plotted that, and we'd expect that we'd get a diagram that looked like a ray fan. The next part of the lab, we found the longitudinal spherical aberration, basically keeping the microscope focused on the marginal focus and sending a ray through the top right here, and then moving the laser down and moving the microscope back until we got to paraxial focus. One main problem that we ran into was that our micrometers didn't have enough room. You know, through this little area, it was fine, and we'd move the micrometer and we'd catch the laser being focused onto the axis, but when it got to paraxial focus, it jumped really far, and we had problems getting our readings, and some of our data was a little distorted because of that, because we had to move the rail slide, and then that kind of distorted our micrometer readings. So we were a little confused on what we were getting as far as the readings on the graph, but our final longitudinal spherical aberration was evaluated.
Alright, so here I'm going to talk about the setup that we used for this lab. We have two rails that we align perpendicular to each other. We have our laser coming in through an aperture pentaprism. We have a Hartman mask in our lens, a microscope, and then a viewing screen. Alright, for our to deviate the beam from one rail to the next, we use a pentaprism. Pentaprism has one less degree of freedom than a mirror that we need to worry about because it will always deviate the beam by 90 degrees. We used an aperture to stop down the size of our hole because the size of our beam on the Hartman mask was too big, and it was going, a single beam was propagating through multiple holes, so we stopped down the size of the beam so that most of the power would only pass through a single hole. And for our microscope objective, we used a large NA to try and pass more of the light through the microscope, and so that we can see it out on the viewing screen.